This is the second of the lectures on chapters 1 and other introduction. Okay, so in this brief lecture, all we're going to do is look at the solution of problems using data supplied in various systems of units. The use of units, when you add numbers, they have to have the same units. So, for example, you can sum forces. Each of these is okay because they all have units of newtons. But if the units are not newtons, then you have to convert them to be the same units. So as long as they're all the same, then you can add them up. When you multiply and divide, the units have to be the same on both sides of an equal sign. Okay, so here we have a force in newtons is equal to the mass times the acceleration. And our units here can add up to kilograms meters per second squared, which is a newton. So in chemical engineering, there's a lot of dimensionless numbers, which means that the units in the numerator have to cancel with the units in the denominator. So you can practice this one for yourself. You're going to be learning the Reynolds number in your Chemie 190 class. And so you should be able to look at all the units and make sure that they cancel. Normally, in an exponential, the units should also cancel. Okay, so let's do a calculation here. So heat capacity can be divided by the gas constant to make it dimensionless. All right, obviously we're talking about the molar heat capacity. Or you have to have your R in units that are the same as the heat capacity. Okay, so here we go. If the units of heat capacity are joules per mole Kelvin, and also the units for R are joules per mole Kelvin, then what are the units for A? Can you answer that? There are no units on A. Okay, the second calculation we're going to do is this, the pressure. The sum of the pressures is going to be the atmospheric pressure. Okay, this is a tank of water, and we have some dimensions here. We've got a height of 25.5 meters. We have the diameter, which is 13.7 meters. And here's the pressure down at the bottom. Okay, and the units are Newton over meter squared. So we're trying to determine what is P. Okay, and so the P at the bottom of the tank is going to be the atmospheric pressure, which is at the top of the tank, which can be assumed usually, if it's not given, you assume it's 1 atmosphere. Then you add that to the density of the fluid times the gravitational constant times the height of the fluid. All right, so here we have a case where you have to make sure that all of your units are the same. So if the atmospheric pressure here is given as 1 bar, density is 1,000 kilograms per meter cubed, it's water, and the gravitational constant is approximately 9.8 meters per second squared. We will convert our 1 bar into pascals here, 1 times 10 to the 5 Newton over meter squared. Then we can sum these up. P is equal to P0 plus rho g h. Can sum all those up, and we end up, it's 3.5 bar. So note here, this is another question. If we put a pressure gauge at the bottom of the tank, what do you think it would read? Okay, does it read 3.5 bar? The answer is no. It will read 2.5 bar. Because the gauge pressure, there's also the same atmospheric pressure on the gauge. So the gauge pressure, you always have to add 1 atmosphere to get the absolute pressure. All right, here's another conversion calculation. This is 2,000 metric tons times 1,000 kilograms per metric ton times day per 24 hours times 3,600 seconds. So the plant capacity of 2,000 metric tons of product per day is going to be the same as 23 kilograms per second. So this kind of calculation you should be able to do easily and have a system so that you do it without making any mistakes.